So as opposed to a permutation, a combination is something where the order does not matter. And we've seen some questions with this already, with lotteries or with picking people for jobs. So it now becomes the number one question you ask when you ever run across any kind of question in this unit. Is this a permutations question or is this a combinations question? The combinations formula, which we've seen already, is just the permutations formula with the order divided out. So you take your permutations formula and divide by r factorial. This line shouldn't be there. The notation is also n over r in brackets. So some special cases. N choose n. You have n items. You choose all of them. The order doesn't matter. There's only one way to do that. Take them all. Okay? And choose one. You choose one item, like 52 cards, choose one card. The order doesn't matter. Well, there's only one. The order never matters. There's only going to be 52 ways to do that. And here is the formulaic expression that explains why 12, that doesn't work, 12 choose 5 is equal to 12 choose 7. If these two numbers add up to this number, they're going to be equal. Because if you have 12 items and you make a group of 5, you automatically leave yourself with a unique group of 7 left. So making groups of 7 is the same as making groups of 5 if the order doesn't matter. The ones that are underlined in squiggle, triple, Z underlining, there we go. Those two numbers, if they add up to 12, or the number that the arrow is pointing at, then those values will be equal. So on your next one, they have the example that 10 choose 6 is equal to 10 choose 4. And if you use the formula, and you will use the formula lots with combinations, 10 choose 6 is 10 factorial over 4 factorial 6 factorial, and 10 choose 4 is 10 factorial over 6 factorial 4 factorial. You can see that they're the same. In the formula, the numbers underneath always add up to the number on top. So if we go back to 12 choose 5 and 12 choose 7, this will be 12 factorial over 5 factorial, and then has to be 7 factorial to add up. This one will be 12 factorial over 7 factorial, and then 5 factorial to add up to 12. And so you can see why they're the same. So one of the applications of combinations is to poker hands. I'm not sure if any of you play poker or have watched poker on TV, but find the number of 5-card poker hands possible. When you get dealt 5 cards, you're like, oh, I would have had a straight if I could rearrange these cards. Well, yes, the order doesn't matter, right? You get your 5 cards, it doesn't matter the order. Oh, I almost have 2 pairs. I almost have a pair, but I have a 9 and then a 6 and then another 9. Well, that still counts as a pair because the order doesn't matter. So if we want to count how many poker hands are possible, there's 52 cards. Each unique group of 5 cards makes a unique set of poker hands. So if you go to your calculator, go over to your choosing, there's almost 2.6 million different poker hands. So I'm going to show you something. I've got a deck of cards here. I'm going to pick 5 cards at random. 1, 2, 3, 4, 5. Get ready to be amazed. Okay? We have an 8 of diamonds. a 3 of clubs. I know the excitement is building. The Jack of spades. The 10 of clubs. And the Ace of clubs. Wow. Take a good look. You will probably never, ever experience this again in your life. Because the chances of me getting this poker hand is 1 in 2,598,960. It's really rare, this poker hand. But unfortunately, where does this rank in poker hands? As, like, pretty bad. I have just single cards. I have a high ace, but that would be it.
You got like a jack kicker.
So it is not a very good poker hand, but the chances of me drawing this exact hand were just as likely as drawing a royal flush in spades. But because this exact hand is 1 out of the 2.6 million. It just happened to be one that doesn't matter. We're going to find out why some poker hands are better than others and how to count them later on. But right now, we find out that maybe one of the reasons poker is interesting to play is because there's so many different combinations of hands possible that you can play a long time without getting the exact same hand again. A committee of 2 boys and 3 girls is to be selected from a class of 15 boys and 18 girls. So here we have a committee. You would ask yourself, does the order matter? I don't like my committee. Oh, we'll change the order. It's still the same people you're working with. And so you have 2 decisions that need to be made for this committee. You have to choose boys and you have to choose girls. There are 15 boys. You have to choose 2 of them. There are 18 girls. You have to choose 3 of them. The number one thing that happens in this question is students get mixed up if this is a cases question or a decisions question. You have to now figure out, am I going to multiply between here or am I going to add? If it's cases, you add. If it's a decisions question, you multiply. Okay? One of the things I use to figure out that I have to multiply here is I have to, if you're doing cases, you would have, after the first one, a complete committee. Do we have a complete committee of 2 boys and 3 girls after our first decision? No. We only have a complete committee after we put both decisions together. So that means it's not a cases question, but you would multiply to get your answer. Well, you would multiply here because this isn't a full case. We add when it's cases, and here we're getting a committee of 5 people. So if you had counted committees of 5 people in different ways, then you would add them up as cases. This will often show up on multiple choice looking like this, just using your formulas. So 15 choose 2 would be 15 factorial over 2 factorial, 13 factorial, and 18 choose 3 would be 18 factorial over 3 factorial, 15 factorial. On a multiple choice, could you see something they could simplify here? Right? The 15 factorials could cancel out, right? So in a multiple choice, this might have been simplified further, and you'd have to recognize that. But just using the formulas, this is what you would do. And you could type this into your calculator to find the exact answer. A group of students must be separated into 3 smaller groups. 8 students in group A, 5 students in group B, and 7 students in group C. How many ways can this be done? Well, here, it's not going to be a different group. if I just change the order in your group. You're still stuck with the same people. You say, I don't like my group, and I say, well, just rearrange yourselves in your group. Well, it's still the same group. Okay? There's 3 decisions that need to be made. You need to decide who's going to be in group A. How many choices would you have for the people being in group A? There needs to be 8 students. Order doesn't matter. You have 20 students in total. You need to choose which 8 go into group A. Mainly calculator, yes, unless the numbers are small. B. How many ways can we choose group B? Choose 5. Why 12? Because you've already chosen 8 people. You're an A. You can't un-A them and make them B. And then group C, right? If this was your class, they said we're going to make 3 groups. Group A, 20 choose 8. I choose my group A. I choose my group B. How many ways are there going to be to choose group C? 1 way, right? 7 choose 7. If you haven't been chosen, you're one of the 7 people left, you wouldn't go, ooh, I wonder what group I'm going to be in, right? You know that you're going to be in group C in the end. So you get 7 choose 7, which is equal to 1. Would we get a different number if I did the groups in a different order? So I would like someone to type this into the calculator and find out. And then we're going to try and say, let's say we picked group C first and then A or B. You multiply them, yeah. If you did group C first, and then what do you want to do, A or B? A. Brum, brum. Okay. So if you did group C first, you'd have 20 choose 7. And then group A, there's 13 people left. You need to choose 8 of them, and then 5 choose 5. I want to know, do these give us the same number, or do we have to consider which group we pick first? What does your gut say? Should they be the same number, or are they going to be different? Should probably be the same. Right, so they should be the same. Has someone typed them in? Are they the same? Or do I have to do this mental math? What? Some people got them the same. Some people got them different. What did you do? That is a 13? Oh, no. Okay, we're good. Okay. Notice what happens if you go to your formulas. 20 factorial over 8 factorial, 12 factorial. Then 12 factorial over 5 factorial, 7 factorial. And this one's 1, so I'll just write that. Okay? This one would be 20 factorial over 7 factorial, 13 factorial. This one would be 13 factorial over 8 factorial, 5 factorial, and this one is 1. Here, my 12 factorials cancel. Oh, that's not a 12. My 12 factorials cancel out. Here, my 13 factorials cancel out. So my final answer becomes 20 factorial over 8 factorial, 5 factorial, 7 factorial in both cases. What does that answer remind you of? Cynthia's last name? Kind of. Does it look like an identical objects question? Could we solve this as an identical objects question? Yes, we could, because you could think of this as having 8 A's. you could then have 5 B's and 7 C's, which would be 20 factorial over 8 factorial, 5 factorial, 7 factorial, the same answer. Why would this work? Well, if you arranged your class from shortest to tallest and then said every different rearrangement of these letters makes different groups of A, B, and C, then you could give each arrangement to the class and you would make all the different groupings possible. So the thing with permutations and combinations is sometimes how you envision solving the problem might give you different results. I think using combinations in this case is easier than using the identical objects. Find the number of poker hands with no clubs. So in a deck of cards, there are 4 suits, 13 of each of those suits to make 52 cards in total. So there would be 13 clubs, and there would be 39 that are not clubs. Now, if I took my deck of cards and I started taking out the clubs, okay, so I'm working here, taking out all the clubs. Joker, club. There we go. Now, be prepared to be amazed. I'm going to shuffle these remaining cards. And Tayan's going to get 5 cards. He picks them, so it's not like I'm setting this up. Okay.
Oh, this is a good hand.
Did you get any clubs? No. I am amazing. How did I do that? You think? Okay. Wow. You think I could do that again? Let's see. 2 times in a row. Pick 5 cards. Oh. Did you get any clubs? No. Yes! I did it again. How do I keep doing this? Because there's no clubs in the deck, right? So if I want to count how many poker hands have no clubs, one of the ways I can do it is just do this over and over again. I could take the clubs out. I now have 39 cards. I still choose 5 of them. That still makes a poker hand. Will any of those hands have clubs in them? No. No. The exam will not have anything to do with gambling. It's true. So even times that they've had like dice, instead of calling them dice, because some people might think that has to do with gambling, they have used questions with dice, but they've referred to them as cubes, numbered from 1 to 6. There you go.
And this got short us like deal dash.
Okay, so this is a very pretty number. Has anybody typed it into their calculator? I really like this number. 7-5? 5-7, 5-7, 5-7. Oh, such a pretty number. It's pretty. Okay. Yes. Yeah. All right. So now, part B. In part B, I am going to be a salesperson trying to sell you correct solutions. I'm going to present to you 3 solutions, of which I am going to sell to you that each and every one of them is correct. However, I'm not going to tell you if all 3 are correct, if 2 are correct, 1 are correct, or maybe I'm a really good salesman and none of them are correct. I'm just playing around with you. So you have to decide. I'm going to present all 3 solutions, and you have to decide which ones you think are right, or if you think none of them are right. But I'm going to try to convince you, because this is what your brain does during the test. Your brain says, yeah, I think this is a good idea. You should do this. Right?
Never a good idea.
Right? And then you do it going, yeah, uh-huh. Right? So you need to develop the counter brain that goes, yeah, I don't know. You have that too? Okay. So here are, don't write these down. Well, you can write them down in the end if you want. Here are 3 solutions to this question. Okay? Find the number of poker hands with at least 1 club. So I have my deck of cards here as a visual. I've already taken out these 13 cards. So if I want to have at least 1 club, what I'm going to do is I'm going to take these 13 cards that have the clubs, and I'm going to choose one of them. 13, choose 1. That way, for sure, I have 1 club. So I take a club out, chose 1. Now I'm going to take the remaining 12 cards, put them back in the deck, and mix them up, and pick 4 more cards. Because that means I could get more clubs, but there's also a possibility that I don't get any more clubs. But since I have 1 club already, I will be guaranteed to have at least 1 club. So if I put the other 12 cards back in the deck, now I have 51 cards left, and I choose 4 more of them, giving me 5 cards, and I'm guaranteed to have at least 1 club. Method 2. Method 2, it's got my 13 cards here. I already know that all the poker cards in the world are 52, choose 5, because we figured that out already. And I just counted in A that there was 39, choose 5 with no clubs. So if I use the NOT strategy and take all the poker hands and subtract the ones that have no clubs, I'm going to be left with poker hands that have at least 1 club. And sales pitch number 3, I'm going to use cases. I'm going to count the case 1 with 1 club. I have my 13 clubs. I choose 1 of them. I have my 39 other cards. I choose 4 more. This will count all of the hands with 1 club. Case 2, I count all the hands with 2 clubs. I take my 13 cards. I choose 2 clubs. I take my other 39 and choose 3 more. How many cases I'm going to have? Next, I'll do 3 clubs. 13, choose 3. 39, choose 2. Case 4. 4 clubs. 13 clubs, choose 4 of them. 39 other cards, choose 1 other. And finally, case 5. With all 5 being clubs, 13, choose 5. I figure out each of my cases separately, and I add them up in total. And since I counted how many hands have 1 club, 2 club, 3 club, 4 club, 5 club, adding them up will be at least 1 club. So I hope I was really convincing that all 3 of them are right. And now I leave it to you to argue. What do you think? So it cannot be the first one because the number is more than the number of poker hands. So now we have to come up with why the logic went bad. What happened in the first one that made it go bad? I will tell you that both the second one and the third one do work. Yes. Right. Actually, I might be lying because if I take a student's kidney, I'd probably get fired. So. All right. I just have a knife from the cafeteria.
Plastic.
That'd be a lot of sawing. Anyways. So what went wrong in the first one? Didn't it seem good? Like, I chose a club.
No, it just seemed kind of weird.
I chose one club. Let's say I chose this one. What is that? The 5 of clubs. So let's say one example is I choose the 5 of clubs. And then I put the other 12 cards back in the deck. And I could choose 4 more cards. So I could have chosen Ace of Diamonds, King of Hearts, 3 of Spades, and what else could I have chosen? Maybe another club. Maybe the 7 of clubs. This would be counted in that method. Why is this method bad? Well, if I did it again, what's another club I could have started with? Oh, the 7. And then I mix the other 12 cards back in, and I could have picked the Ace of Diamonds, the King of Hearts, the 3 of Spades, and the 5 of Clubs. What's the problem? I already counted that one. But in this method, I counted it again. And in this method, we inadvertently added order because there was overlap between this decision and this decision. Because we could have picked a club first and then picked another club later, those get recounted. How much did we recount? Over 1 million extra. A lot of extra counting. And so anytime that we are doing multiplication and decisions, we have to make sure that our decisions don't overlap, otherwise we create order when we don't want to. Like in choosing boys and girls, for those decisions that didn't matter because we weren't having any overlap between them. You didn't get picked as committee first, so you can't just try again later. That's why the third one works. The third one works as cases because there's no overlap there. We're choosing clubs, we're not choosing clubs. Then we're choosing 2 clubs and then not choosing clubs in the second one. And so therefore each of those counts what we want it to and it adds up correctly.